Thank you, Shay, for the introduction to the heliophysics big year thing. And then we will have our seminar today from Dr. Milan Gošić. Let me introduce our speaker today. Dr. Milan Gošić is a research scientist at Bay Area Environmental Research Institute and Lockheed Martin Solar and Astrophysics Laboratory. He got his PhD of astrophysics from University of Granada, Spain in 2015. During his PhD, he visited Lockheed in 2013 and 15, and after graduation, he joined Lockheed Berry. Dr. Milan Gošić has been working on the temporal and spatial evolution of small-scale solar magnetic fields and their impact on the energetics and dynamics of the solar atmosphere. His serious works on internetwork flux have shown that small-scale magnetic fields are the main source of magnetic flux in the quiet sun and may also locally heat the upper atmosphere. Today, he will give a talk about spatial temporal evolution of the quiet sun magnetic fields and their role in the chromospheric heating. Thanks to Milan again, and you have your seminar time now, still up to an hour. Thank you.
Thank you, Rayton. First of all, thank you for inviting me to give this talk. And yes, I will be talking about the spatiotemporal evolution of the quiet sun and magnetic fields and their role in the heating of the upper solar atmosphere. But it actually comes down to the importance of the internetwork fields about the solar magnetism in general. So to start, I will first describe what the quiet sun is. So if we take a look at a full disk magnetogram, for example, in this case taken with the HMI, shown on the left side, we can all easily notice where is the active region, and those regions have strong magnetic fields with a lot of fluxes brought to the solar surface. But outside of the active regions, we have, and of course outside of the coronal holes, we have the so-called quiet sun regions. And the word quiet here is for the historical reasons, because at the beginning, when we started looking at the magnetic fields on the sun, we didn't really see a lot of activity outside of the active regions, and therefore quiet. But as instrumentations and telescope improved with time, we started noticing that the quiet sun is not really quiet. So the first and most obvious thing that we can notice in the quiet sun are the strong network fields that organize in kind of a network pattern. And one example of this quiet sun region is shown on the in the enlarged picture here. And here, yes, we can see a lot of smaller scale magnetic fields, and we can also zoom in further this picture and focus on this blue square. This region is shown on the right side. So here we have in the photosphere, in HMI magnetogram, the same supergranular cell, and we can see clearly the strong network patches around the edges of the supergranular cell. And if you look at the AIA observations and move from the chromosphere towards the corona, we do not have a lot of emission inside of the supergranular cell between the network structures. But there is some emission going on above the network fields, and especially when we have the cancellations of the opposite polarity magnetic structures, like on the southern part of the supergranule, where we have emission both in the chromosphere and in the corona. Other than that, we can see that only it's background emission. So another even closer look at the same supergranule shows us on the left side an HMI 12 minutes magnetogram. And again, the only thing that we can really see clearly are those network patches occupying the edges of the supergranular cells. And to really see whether there is a magnetic field inside of the supergranular cells, we have to use high resolution and equally, at least, if not even more important, high sensitivity observations to detect the weak fields that we can see, for example, in Hinode NFI observations. So on the right side, we have an example of NFI magnetogram, and now we can see small scale flux patches inside of the supergranular cells. So by taking only HMI magnetograms, we cannot really see weak and small quiet sun fields. That is the internetal fields inside of the supergranular cells. So just briefly, some basic properties of the network fields. The network fields are strong kilogauss fields located around the edges of the supergranular cells. They can be visible on the solar surface for many hours or even days. And one interesting aspect of the network fields is that the total amount of flux located inside of the network is actually comparable to the flux that we detect inside of the active regions. And in addition to the network fields, we also have those dynamic small scale fields that we can see moving around in the movie on the right side. Those internetal fields are located inside of the supergranules. They can live between 5 and 7 minutes on average. There are much stronger internetwork fields that survive up to 5 to 6 hours, for example. On average, they are small, like 1 arc seconds large. And the amount of flux brought by these fields, individual flux patches to the solar surface, is about 10 to the power of 18 Maxwells, with the lower limit being actually governed by the type of observations that we have. With the newer telescopes and improved sensitivity, the lower values can be even 10 to the power of 15 Maxwells. So if internetal fields are weak and small and we do not see a lot of activity above the supergranules, why do we care about internetal fields at all? So one reason is that if one would take an image of the sun, a magnetogram, most likely about 50% of the detected flux in that case would be in the form of internetal patches and the rest in the form of network. And the other reason, I would say even more important, is that since internetal fields occupy the interior of supergranular cells, they practically appear everywhere on the sun. And since we have a lot of them, they may actually they may contain a huge amount of magnetic energy stored in the photosphere, and that energy somehow has to be dissipated, and part of that energy we can expect that is used to heat the upper solar atmosphere. So what do we know about the internetal fields at the solar surface, how they evolve? So since internetal fields are small and weak, they are easily dragged by convective motions. And the most dominant flow pattern in this case would be a supergranular flow. If we compare the radial velocities of the magnetic patches inside of the supergranules, radial in this case means that we are looking at the component of the velocities from the center of the supergranules toward the network. We can see that radial velocities of magnetic elements actually coincide quite well with the supergranular flow pattern, meaning that the supergranular flows can take those magnetic elements from the interior of supergranules and push them toward the network structures. There are a couple of more aspects of the motions that may affect the trajectories of internetal fields. First of all, there is also influence by granular motions. They can drag around at least those weaker internetal fields. But there is also a random component, random jitter of the center of mass, or better to say, center of flux of the individual patches. And this happens because magnetic elements in the photosphere, as they evolve, can interact with each other. And this means they can merge with the same polarity magnetic features, or fragment or cancel with the opposite polarity elements, and all that would affect their trajectories. But if you look at the individual trajectories in the movie on the right side, one can notice that all these elements in principle have a tendency to move toward the network structures. And once they reach the network regions, they can do, in principle, two things. One is they have to interact with network, and then they can either add flux to the network, or they can remove flux from the network regions. Adding flux goes through the merging process, and removal from the cancellations, where we can expect to have a lot of reconnections of the magnetic field lines. So in the movie shown on the left side, we have network marked with the blue contours. The magnetic elements with the red contours indicate those that add flux to the network. And green contours magnetic elements remove magnetic flux from the network through cancellation processes. And if we now calculate the total amount of flux that is brought from by internetwork fields to the network, we can see that the same amount of flux generated and carried by internetwork fields is equal to the network, and that is achieved in only about 10 hours. If we account for the type of interactions between internetwork and network fields and calculate how much flux is added to the network and how much flux is removed, we can conclude that, as shown on the right side with dash line, that replacement time for the network flux by contribution of the internetwork fields would mean that internetwork can completely replace the network flux in about 1 day or even less. In other words, this would mean that internetwork fields by themselves can actually govern the evolution of the quiet sun magnetism. There are a couple of more aspects of the interplay between the convective motions and the magnetic fields. What we usually detect at the edges of the supergranules, as shown in this figure here, are the vortex flows. So on the right side panels, we have the enlarged patterns, the streamlines of the flows around the edges of the supergranular cell. And we can see how these vortex flows look like. What would happen in those vortex regions is that vortex flows can actually help concentrated and intensifying magnetic fields in these areas. Here is an example of long-lasting for almost a day vortex flow that is occurring from time to time at the same region. And when the vortex flow gets weaker, magnetic fields have more freedom to evolve as they please. They can fragment. When the vortex flows get stronger, they can bring magnetic flux to the same region, to the same area, and intensify them. And the question would be, okay, why do we care about this interplay between the magnetic fields and vortex flows? Well, the reason comes from the theoretical models. In one of the papers published by Silva and co-authors, it looks like the vortex flows can actually appear everywhere on the sun, not only at the edges of supergranules, but also in the intergranules, on the granular scales. And vortices, in this case, can actually intensify magnetic fields in the sinking points, which leads to formation of the twisted flux tubes in the photosphere. And then those flux tubes can actually also help the vortex flows, and they can propagate the rotational motions along the magnetic field lines to the upper solar atmosphere, at least to the chromospheric heights. And in addition to those rotating motions of the chromospheric structures, we would also have a component of the swaying motions. which is related to the alphenic waves. Also from the theoretical models, generation of the Lorentz force due to the presence of the twisted flux tubes can actually lead to small-scale jet-like ejections. And those ejections are attributed to the spontaneous upflows in vortex tubes. So this means that actually there are different ways how the energy can be channeled from the photosphere to the chromosphere. And one of the quite abundant agents to transfer this energy could be those vortex flows in the intergranular lanes. So how these internetwork fields appear at the solar surface at all, and can we conclude anything about their origin? Where do they come from? So the first mode of appearance of internetwork fields is something that we would expect to happen on smaller scale, just like on larger scales, meaning that we would have the opposite polarity flux patches emerging on the solar surface and separate from each other, similar to active regions. And this is really what happens. So for example, in this example here, the middle row shows the linear polarization signal. And the first thing that we would see when new loops appear on the solar surface is the linear polarization signals that shows us the top of the loops. And then at the flanks of the linear polarization signals, we would detect circular polarization, opposite polarity foot points that separate from each other. And normally, in the quiet sun, new magnetic loops appear at the edges of the same granules or above the granules. In addition to this mode, we also have something that we call unipolar fields. And those fields are clearly, by the name, in disagreement with the Maxwellian equations. So we have to figure out how to explain the presence of unipolar fields on the sun. And normally we detect unipolar fields in intergranular lanes. One can argue that those fields appear on mesogranular scales, whether they exist or not. And what may happen is that, as shown on the left side, in the case A, is that when magnetic bipoles, the loops, appear on the solar surface, one of the foot points would be strong enough to surpass the sensitivity threshold in our observation, so we would detect that foot point. And the other foot point can be more dispersed and weaker, so it would be below the detection level in our observations, and we would simply miss that foot point. The other possibility is merging or coalescence of the same polarity flux that is accumulated in intergranular lanes. And then when this flux is accumulated and intensified, it may appear in our magnetograms as a new magnetic element. The problem that I see with the presence of unipolar fields is that we cannot really know, at least not from the observations, whether these unipolar fields really represent formation of new flux, similar to the case A, or it's just the flux that sits there in the photosphere and is recycled and intensifies and gets weaker and so on. And that is important if we want to understand what is the origin of the internetwork fields. So there are a lot of papers discussing this topic. The results differ a lot, and the reason is because we normally use different observations that have different resolutions, sensitivities, cadences, and so on. And I think the crucial aspect is actually that we all used different methods to identify magnetic fields in our observations and then to track them. And we try to contribute to this open question and answer the question how these fields appear on the solar surface and what is the fraction of the total amount of the quiet sun flux inside of the supergranular cells is due to the bipolar and what part is due to the unipolar magnetic structures. And to do this, we use the Hinode NFI observations with the highest sensitivity that we possibly could achieve. It was 4 Gausses only. And we didn't have linear polarization, so to study the connectivity between magnetic patches, we used magnetofrictional simulations to extrapolate the field lines above the photosphere, and in that way study the connectivity between magnetic elements. And we had a couple of more requirements, like we would expect from the newly emerging fields to appear as opposite polarities food points that more or less have the same amount of flux. They appear above the same granules or at the edges. They move in the opposite directions. In terms of the magnetofrictional simulations, they would be connected, at least during the emerging phase. And we also try to identify all these magnetic elements and track them practically semi-automatically, meaning that we automatically track the individual patches, but we use different methods how to identify them. And by visual inspection, we actually interfered with the tracking, and whenever it was necessary, we switched to a more appropriate method of the identification. This is an example of the detected new loop. So we had in the magnetograms, the middle panel, emergence of new food points. We didn't have the linear polarization, but we can see on the right panel that those magnetic elements appear at the edges of the same granules. And on the left side, we have magnetic field lines derived from the magnetofrictional simulations that show the connectivity between the food points. And the connectivity can be established by the moment when magnetic food points start interacting with the surrounding network patches and cancel, and most of those lines get reconnected. So in total, we had a long sequence of almost 1 day of NFI magnetograms, and inside of this red circle that should indicate the interior of the supergranular cell, we try to detect and track every single magnetic loop, individual magnetic loop with the 2 foot points, and also clusters of the magnetic loops, and see where they appear and how much flux they bring to the solar surface. So now if we integrate with time and see where magnetic elements, whether bipolars, loops and clusters, or unipolar fields appear, and plot them on the top of the average magnetogram, we can see that on the left side, that the loops and clusters, so bipolar fields, appear more or less just like unipolar patches uniformly across the supergranule. And this is in disagreement to some extent with the previous results that suggested that internetwork fields may have a preference of appearing closer to the network fields. So in terms of the total flux present inside of the supergranular cell, the contribution from unipolar features is quite low, and it's pretty much constant with time. The bipolar features can actually, the flux from bipolar features can vary a lot, and we can detect a lot of flux being brought to the surface in the form of bipolar internetwork fields when strong loops or clusters of internetwork fields appear in the photosphere. In terms of percentages, we established that about 70% of the flux detected in this particular supergranule is due to the bipolar fields, and about 30% due to unipolar fields. But the contribution from the bipoles change with time, and it can drop down to even 20%. So another important aspect of the flux appearance nature of the internet of fields is the emergence or the appearance rate. And for several supergranules that we used and tested, it turns out that the appearance rate is on average around 120 maxwells per centimeter square per day. And 55% of that is due to the appearance of bipolar fields. So this number by itself, I would say, doesn't mean a lot if we do not put it in the context. And the context is that according to Hinode NFI observations, at least, the appearance flux rate in active regions is only 1 Maxwell per centimeter square per day or less. So in the quiet sun, we have much more flux brought to the solar surface every day. Whether this flux is really new flux, that's still an open question. And what happens to that flux, we still do not fully know. Most of these flux just disappears in situ or is canceled with the opposite polarity patches. Some of these fluxes are brought to the network, and then we still have to understand what happens to that flux inside of the network regions and how it is removed from the solar surface. Still, one more slide about the appearance of bipolar fields. If we calculate the orientation of these bipoles by comparing calculating the angle between the magnetic axis between the foot points against the solar equator, we do not see any preferential orientation for the bipolar structures, and that can give us an idea of about the origin of internetwork fields. So, just like for the active regions, we also expect that the quiet sun fields are generated by global dynamo, or in this case, also possible mechanisms is local turbulent dynamo. But according to our results, the local dynamo looks like a more probable mechanism. And once these internet fields are brought to the solar surface, some of them can actually hit the upper solar atmosphere. So there are two aspects of this heating, how they actually can, how the internet fields can hit the chromosphere. One of them is through the emergence to the upper layers, and the other one that we will see later is through cancellation or reconnection of the magnetic field lines. So in this example here, we have SST observations of an emerging internetwork, well, either cluster or 3 individual loops. On the left panel, we have the convective motions. We have the evolution of the granules, and during the emergence, we have a clear pattern of the elongated granules. We have the upflows in the photosphere, and also the appearance of linear polarization signal suggesting the top of the loops. And in the magnetograms, we can see the evolution of the opposite polarity foot points separating from each other, and eventually they reach the network structures and interact with the network fields. The field strengths for these particular magnetic features is between, let's say, 500 and 800 Gausses. We can also look at the same type of the observations. On the left side, we have magnetic field strengths from the inversions. We can clearly see again the evolution of the foot points in the photosphere, and also in the upper photosphere by using the magnesium 1B2 line. And if you look at the core of the calcium 2 line, 8542, we can see a lot of strong signal cospatial with the photospheric foot points, and also formation of the loop-like structures between the foot points, which may indicate that these particular emerging loops actually reach the chromospheric heights. Another chromospheric observable that we can use to further see if we really see, we can detect the internet of fields in the chromosphere comes from the H-alpha observations. And at the beginning of this sequence, we can see a lot of H-alpha fibrils connecting the network structures. But then the internet of fields appear from below and push those ambient network fields up. And an interesting event that happens here is actually the appearance of blue shifted H-alpha structure. And for these particular kind of structures absorbing chromospheric features, it could be understood as the acceleration of the chromospheric material, which is driven by strong thermal and magnetic pressure gradients during the expansion of the newly emerging fields from below. And this interaction can actually lead to formation of cool jets and subsequent shocks in the chromosphere. Another type of the observations to really see that something is going on in the chromosphere and even in the transition region comes from the iris observations. So again, in this movie, we have the evolution of the loops, the foot points in the photosphere. And then we have appearance of bright structures in the iris slit jaw images in the magnesium and silicon-4 filter, showing us the brightening cospatial with the foot points and also formation of the loop-like structures between the foot points. But the main information here comes from the iris spectra, where we have the strong emission in the transition region lines, in the carbon-2 and silicon-4 lines. So I will pause this movie, and here we can take a look at in details the shape of this emission as the slit is crossing above the emerging fields. And what we can see here is first we have blue shifted profiles that transition from the southern part of the region to the northern part to the red shifted profiles. Very strong emission, and if you look at the individual shape of the carbon-2 and silicon-4 lines, we would see they are non-Gaussian, very broad, with the wings extending up to the 100 kilometers per second or even more. They are multi-component, some of them are double-peaked, and usually such profiles are associated with the reconnection of the magnetic field lines in the upper chromosphere transition region. We would have something that can be explained as bidirectional flows generated during the reconnections. And the triangular non-Gaussian profiles are also associated with plasma-mediated reconnections. In other words, in this particular case, we can witness that internetwork fields, newly formed loops, can actually reach the chromosphere and transition region and heat the atmosphere there. If you look at the iris squared inversions of the magnesium iris magnesium 2 line, here inside of the white box, we can see the temperatures. And the most obvious thing is that the temperature is much higher above the network structures and inside of this white box where the new fields appear. So on the right side, we have the zoomed in picture of this region, and we have the larger temperature above the foot points and along the field lines, and also we have the line of sight velocities indicating the upflows along the top of the loops and downflows above the foot points of the emerging fields. So from these observations, we can conclude, as I said before, that internet of fields, at least those stronger ones, between 500 and 800 Gausses, can reach the chromosphere, and they can locally heat the solar atmosphere. But the question is what would be the global contribution? And to answer that question, we try to detect all the internetwork loops and clusters, again, in NFI observational sequence in the magnetograms. In this particular case, we have also linear polarization to see the top of the loops, which help us identifying the magnetic bipoles. And we try to associate all those detected bipoles to the chromospheric activity as seen in iris observations in the mostly in the silicon-4 filtergrams. We also had a couple of loops detected under the iris slit. So for this only 7 bipoles, we have a temperature map, and we can see that 3 of them can be associated with increased temperature, like B4, B5, and B1, either through the direct interaction with the ambient field due to emergence, or these fields can also interact with the pre-existing fields in the photosphere and the lower chromosphere and cancel with the opposite polarity patches, and through that cancellation contribute to the heating of the chromosphere. But the problem is that from our results, it looks like only about 30% of those bipoles can reach the chromosphere and heat the solar atmosphere. If we consider also those loops detected under the iris slit, even though it's really a small sample, then this contribution comes to 40% of the loops hitting the chromosphere. But it's still locally in the nature. So we know that we for sure miss a lot of those bipoles appearing, first because of the sensitivity that wasn't sufficient. But I think that to really see all of those weak fields and what they can do in the photosphere and possibly in the upper layers of the solar atmosphere, we have to wait a little bit more longer and use the observations from the new generation telescope like Solar Orbiter, DKIST, MUSE, and EST. And the final part of my presentation is another aspect of the heating of the solar atmosphere by the internetor fields, this time through the cancellation process. And here we have an example of canceling event. So in the magnesium line recorded with the SST that shows the upper photosphere, we can see the opposite polarity patches approaching each other, and then they start canceling. And we have, after that, the same thing happening in the lower photosphere. So we have a cancellation of the opposite polarity patches, and we also detect the linear polarization signal. And if we assume that this is due to the reconnection, we can interpret this as reconnection that is happening in the upper photosphere, lower chromosphere, and we have a formation of the new loops. Set of those new loops go upward, and set of them go downwards towards the photosphere. And we also detect brightenings above the canceling regions in the calcium 2 line and the iris silicon 4 and magnesium 2 filters. If you look at the inversions of the iris magnesium 2 line again, and take a look at the temperature map, we can see that the temperature is increased above the canceling region, where we can also detect line of sight upflows, meaning that most likely we do see here the reconnection of the field lines, and part of those loops are going upward, heat locally the chromosphere, and we do not see the how this upward moving plasma falls down. We do see here at the end the downflows. But this is actually from a different region because the slit was moving across the canceling site. So we also here try to detect in the entire field of view of the available field of view in the SST observations, all the magnetic features that cancel, and try to associate them with brightenings in the silicon-4 filtergrams. So in this particular movie, magnetic elements that have associated silicon-4 signal above them have a green circles around them, and those without silicon-4 signal have the red circles. So what happens is that also for the cancellations of the inter network fields, pretty much the same thing happens as for the emergence. We have a local contribution where the inter network fields can hit the chromosphere. But if we take into account the abundance of these structures, we still do not see enough of them to globally support the chromospheric heating in the quiet sun. And to finish, I would briefly summarize the presentation. So what we know about the inter network fields is that there are a lot of them on the sun. They occupy the interiors of the supergranular cells. And even though they are weak and small, they may contain a huge amount of magnetic energy that can be used for the heating of the chromosphere. They are coupled to the dynamics of granular and supergranular cells, which leads then to contribution to the network, vortex flows, and so on. Most of those flux detected in the photosphere are due to bipolar features, which tells us that possible mechanisms or for their formation, their origin, can come from the action of the local turbulent dynamo. And inter network fields can locally heat the upper solar atmosphere, but we still do not see enough of them to have a clear picture whether they can actually maintain globally the heating of the solar atmosphere or not. And that would be all I have prepared for today. Thanks.
Thank you, Milan. We have hands raised from the attendee section. Jan, do you want to ask question?
Yeah, yes, this is Lars Velgaard. I have a question. How much of those fields end up in the solar wind?
That's a good question, but I do not have an answer to that question. And to be honest, I actually plan to attack that problem in near future. So my expectation is that, and unfortunately, that's the best answer I can find for you now, is I would expect a lot of interactions between the quiet sun fields and probably the fields in the coronal holes at the edges, if we are really capable of understanding and finding where these borders between the quiet sun and the coronal holes are. Yes, but in other words, I do not really know that answer.
Thank you.
Okay, and I see several hands raised. So Jan, and then Wei Liu, and then Irina. So Jan, have you already finished your question? Ask your question. And then Wei Liu, are you able to speak up in the attendee section? You should be able already be allowed to talk.
I muted myself. Can you hear
Okay.
us?
Yes, I can hear you now.
Hi, Milan. Just a curious question. Do you see similar features in the filament channels? Or I was wondering if some similar features could happen in filament channels, and in particular, the cancellation process and how that process would contribute to the formation of filaments.
I didn't study inter network fields that or quiet sun fields that could be associated with filament channels, but I know that There are a couple of papers by Hagener about the ephemeral regions, still small scale quiet sun fields. And those filament channels can actually affect the appearance rates and the evolution of the small scale fields. So I would expect the situation is a little bit different, but I don't know exactly how. But I would still expect that whatever you find inside of the filament channels, you should be seeing a lot of cancellations. And if those fields are strong enough, maybe it's sufficient to trigger, I don't know, some eruptions or something that can disturb the filaments or. Yeah.
Okay. Okay, thank you. And next, Yan, right back. Your hands is still up. Do you want to ask the question? And then I'll go to Irina. Okay, maybe Irina first.
Okay, can you hear me?
Yes.
Oh, cool. First, thank you very much for very interesting presentation. Just more speaking from simulation side. And just want to say we did simulations and published results more than 10 years ago, something like this. And what you discussed about vortex tube dynamics, interaction, subsurface and atmospheric flows, actually it was shown. But my main point why I decided to speak up actually, because you start discussing about heating in chromosphere. And our simulations actually showed what vortex tube dynamics in presence of magnetic fields can increase temperature in chromosphere and can contribute to chromospheric heating. And just last thing, I want just to comment. Also, maybe you will respond to this regarding reconnection in the chromosphere. Actually, at least what I see in simulation, sometimes it is very tricky to say if you have reconnection or not, because even if you have two opposite polarities which merge together and give you it looks like reconnection, but maybe not, maybe just change topology of magnetic field line. And we need to be very careful with interpretation.
Yes, I absolutely agree. Cancellations are very tricky to interpret. Most of those cancellations are not related to reconnections. There might just be loops going upward or downward without doing really nothing special. That's why, for example, if we use an estimate of how much of the cancellations in the entire field of view that it's shown in one of the movies. Sorry, let me. I suppose you do not see actually now.
May I ask a following question, just to help to understand this better? Is it possible to reconstruct actual magnetic field? And it may kind of make everything much more clear. I understand it is very complex problem. So
yes, so from this movie, we can see where the cancellation occur, and it's only a guess that whether if we have some activity in the filtergrams in iris slit jaw images, I may say yes, maybe there is a reconnection, maybe not. I cannot be really sure. For those cases where we have also spectra from iris, then maybe we can discuss about it depending on what kind of profiles we'll see in the transition region and whether we can actually connect those profiles to what really happens below. For the inversions and reconstructing the magnetic fields, At least from the SST observations and Hinode, we can do that in the photosphere, but I think that is not enough. We would need to know how the fields look like in the chromosphere, and getting the chromospheric circular polarization in the quiet sun is extremely difficult. The only one that I have, and I can see the foot points in the chromosphere from the internet of fields, is the one I showed for the emerging fields.
Mhm.
I'm not aware of other quiet sun observations showing quiet sun, well, internet of fields in the chromosphere. So reconstructing magnetic fields, I think, would require really more sensitive observations, like hopefully DKIST.
Thank you very much. Very interesting work.
Thanks.
Okay, we have a chat question by Amy, and after Amy's question, we will have Todd and Wei Liu again. Amy, do you want to ask a question? So the question was, were the flux emergence rates given for the bipolar structure signed or unsigned?
It is unsigned flux.
Okay. All right. Thanks. Sorry.
Oh, it's fine.
Okay. Then
Otherwise, I think it would be very small, because the net flux, at least for the bipoles, should be more or less 0.
thank you. And then Todd?
This is Junwei, not Todd.
Oh, okay.
So, for as we know, the supergranules and the network structures, they have lifetimes. So I'm wondering if the emergence rates of the internetwork magnetic field, do they have any correlations with the lifetime, with the phase, phase of the lifetime of the supergranules? Is it more emergence at the beginning, or more emergence during the maximum of supergranules? Is there any correlation of that?
As far as I'm aware, I think there is no correlation. Sometimes emerging fields can directly form the network structures, depending on the phase of the evolution of the supergranules. Newly forming supergranules can be formed directly by the interactions with the newly emerging magnetic fields. At least that's what I know from the NFI observations. Sometimes strong bipoles would appear in the center of the supergranules or the edges. It's not really something that that is constant with time. It varies a lot. Even though for some of the supergranules, the network stayed pretty much stable for almost 2 days. And I think the fact that the amount of flux brought in the bipolar form is more related to possible randomness of the local dynamo than what is coming from further below of the sun.
Okay, thank you. Good to know.
Okay, Wei, you have another question?
Oh, hi, Milan. We again, just follow up on the filament channel. I was wondering if the constellation could have some contribution in terms of the, you mentioned constellation can cause energy release and heating, and also how about mass transport? If heating in the lower atmosphere, like the chromosphere height, would that cause some, push some mass up? You heat the mass and also push them upward into the corona. The reason I'm asking is if this mechanism is relevant, there might be some contribution to the source of mass in the filaments, because those are pretty heavy mass in lifted in the corona. I think it's still a bit mystery where and how those mass get there.
Personally,
or interpretation.
I would expect that at least from some of the canceling features that we see in the photosphere, upper photosphere, you would get some mass transferred from the lower layers to the chromosphere. And this is what we see in one of those, for example, here, you actually see the upflowing plasma above the canceling region. What happens after that to that plasma, I don't know. I would expect it falls back to the photosphere. Whether it interacts in some other ways with the ambient fields, I wouldn't know. I didn't have the observations to look for that. So I can only speak from the perspective of the quiet sun internetwork fields. I don't know what would happen in the filament channel, but I would expect that some mass is transferred from the photosphere to the chromosphere.
Okay, great. Yeah, that's good to know. So I think, of course, the next stage, that's probably another subject. Where does the mass, after being transported from photosphere to chromosphere, then where it goes? It could fall back as ring, or continue to being heated and lifted upward into the corona, and then potentially get somehow channel to those filament channels to form the filaments.
Yes, I agree.
That's hypothesis. But at least you gave me some confirmation. Well, there's the first step is to lift the mass from photosphere up to the chromosphere, being associated with those cancellation, and the flux cancellation happens very often in those filament channels because that's a priority inversion line sits. So that's a pretty piece of information. Yeah, thank you.
I wouldn't expect a lot from HMI observations because there you would see only the stronger fields, network-like structures, or stronger internetwork fields, so you may miss a lot. I wouldn't be even too optimistic to see a lot of those cancellations actually bringing plasma upward, even with the, I don't know, Hinode observations. So it will be really, I think, challenging to detect all of them and quantify how much you have a contribution from such fields.
Okay, thanks. Yeah, thanks for noting the caveat. Yeah, that's all from me.
Thank you. Any more questions? Okay. Then let's thank our speaker, Milan, again. Thank you for the very nice talk and very detailed discussions and question and answers. Thank you again, and hope to see everyone next month at our next seminar.
Thank you very much. Bye.
Bye.
Bye. Bye-bye.